object a logical volume by using, for example, replica or division. Our primary generator action is an user action, a physics list, or I don't know. Wow, I think I put too long time out for this question. Our primary generator action is one and a user action, and is actually the only mandatory action that we have to register. The other user actions that we checked, we implemented yesterday, are optional to run a simulation. A physics list is related to a primary generator, but it's not the same. A physics list is just a list of particles that may happen during the simulation and their processes. Of course, in order to inject some primary particle, that primary particle must exist, must be registered by the physics list. If you try to inject a primary particle that the physics list didn't register, G4 cannot simulate that. How many primary particles must be defined to start an event? 0 or more, 1 or more, or I don't know. So yes, the answer is at least one particle, because the simulation unit, that is the event, starts when we tell the simulation engine what is the first particle. Without particles to be simulated, an event cannot start. Now, a G4 step represents the status of a particle before and after a step, the latest status of a particle being tracked, or I don't know. So a G4 step represents the status of the particle that is being simulated before and after the step. The latest status of a particle being tracked corresponds to a similar object, but is not the same G4 track. A concept, the object in the track object in G4 corresponds to a snapshot of the particle properties at a given time, and that time is in particular the post step. The properties of the track are always the latest in the step. But the step itself, a G4 step, contains information, a delta information, how the particle was before the step and how the particle is after the step. A simulation event finishes when the primary particles are tracked until an end condition. The primary and all secondary particles are fully tracked, or I don't know. So a simulation event finishes when all particles that are being created during the event, that is the primary, that can be one or many, and all the subsequent secondary particles that might be created during the tracking are fully tracked. You remember some of the end conditions are the particles are trying to escape the world, the most top volume in the hierarchy of geometry. The particle can be stopped completely, so no more kinetic energy is available for further tracking, and the particle is stable. The particle can be also be absorbed or annihilated in the material, or we can also kill the particles. But the event finishes when the primary particles and all the subsequent secondaries are fully tracked. Is it possible to simulate more than one run with the same application? No, the application must be closed and executed again. Yes, it is possible by invoking the beam on method of the run manager, or I don't know. Yes, we can simulate several runs within the same application without the need of closing it and launching it again. We can call the method beam on several times, either from the UE command or using a macro file or with the C++ code, but there is no limit on the times that we can start a run with the method beam on. And finally, would you like to take the advanced course? Yes, no, or yet do not know. Okay, well, I think this is a success. Very good. So I will transmit the news to the lecturers of the advanced course that you are willing to do the course. Okay, so this is the ranking. Wow, you were very fast. I'm saying, so thank you very much. This was just a way to do a recap in a more interactive way. And thank you very much to you for participating. So now we can stop and we can start with the actual course. So today I changed a bit the content with respect to previous years. So I will simply review what it was given in previous years. I will then move to the new topic that we will cover in the next half an hour or so. And then we will run, the next topic will be the G4 analysis. It's just a way, either what it was done in the previous courses, or this is just a way to extract information without the need of understanding much how Jam4 works internally. We will also run some validation before the break, and maybe we will have time to spot a bug that nobody noticed so far, and it's an execution bug. So the application runs, but not how we want. Yes, there is.
Maybe a question of the advanced course, like
yes.
On the G4 website, there's like past editions. Do you already know if it will be the same as last year? Or...
You mean if the content will?
Yeah, it's already set the advanced course.
Maybe Gabriele can answer. So there is a question if the content of the advanced course will be the same as in the previous years, or it may change, or if it is already somehow prepared or planned.
In great part it will be similar, but it is somehow tuned every year according to what also you just want to learn. So there will be a questionnaire somehow that will be distributed to people who want to participate, to know what are their preferences, but if they have any topic that may be more touched by the course. But the structurally will be similar.
And I would add to Gabriele's comment that it's difficult to make changes which are very large. We have typically added or subtracted one module. I will say that we did actually have someone introducing the G4 analysis in one of the last 3 years and visualization in another. So we do try and vary it at the edges and also try and adapt some things.
For example, I believe last year in the geometry section, you included some practical notes in addition to the other content. So there is always some feedback and they update the content.
Yeah, the content in general is updated also to the new release. If there is anything in the new release that needs to be noted. Yeah.
Okay, so now we are going to move to to the next point, I will show you the code as it was presented in previous courses. Yesterday, at the end of the day, we try out multi-threading in Jam4, and we noticed that things were not working as we expected, because when we activate multi-threading in Jam4, the user actions that we were registering actually are cloned. Each thread will have a copy, their own run action, their own step-in action, their own event action. So we needed a mechanism, a method to synchronize, to merge the final the individual output from each thread into one single output at the end. To do so, I will show you how it is done, let's say, in the manual manner. We can take a look to the GitHub material, which is attached in the timetable for today. Is one of the links that appear here. So this will bring us to the repository of Mihaly Novak, who developed this course some years ago. We can go to applications and final application. And this, you will find the application that we have been developing these days, including this last step for synchronizing the different threads and providing one single output. To do so, we still will need to declare a custom run object. Sorry, I will go to the implementation. You can see the object G4Run. So far, we have been using the object G4Run from Jam4, but Jam4 offers the possibility to override the object and create our own. In this case, we could create your run class, and in this case, as you see, it has some functionality to accumulate information that is happening during the event, and then a method to merge different G4Run objects, in this case, your run objects. This is how we will have to do it in case we want to implement to do the synchronization ourselves. However, this is a bit it requires a bit of coding, and I thought it would be a good idea to change a bit and present you a built-in module in Jam4 called G4Analysis that can do all this for us. Okay, but still, if you want to try out the code, just for you to know that in this repository, you have the applications in an intermediate state, as it was at the end of Wednesday, and in a final state that is with all the comments that you can imagine, plus the extra class derived from G4Run, and some changes in the run action, just to be able to work in multi-threading. Now we will review the alternative mechanism, and this is what we will implement. It's very short, and you will understand very quickly why it is, for this purpose, is worth it. So the G4Analysis is just a way to store and analyze, and you can put quotes in analyze the simulation data. This module can create some histograms and tuples. And tuples is just the tabular data, because it does not have anything to do with root directly. It can create profiles and directly also the output files, and everything will be done for you. It offers a unified interface for different formats. So maybe you are more familiar with root, but you have also CSV. HDF5 is another option, but you need the corresponding library to be able to export in this format, and XML for the same. You will, I guess, another library for that. And the beauty of this is that the API does not change. You can select the output file, you can select the tuple or the histogram or whatever object you want to store, and G4Analysis will do the conversion for you to the output format, and it will do an internal storage for you without you having to specify anything. The central analysis object, or the central object for this G4Analysis, is the so-called G4Analysis Manager here, and it's just a singleton. So Jam4 will take care for creating and deleting it, and wherever you need it, you have to call G4Analysis Manager.instance, and then you will be able to access it. The typical workflow would be to call the first time in the run action. When creating the run action, we should call the G4Analysis Manager instance at least. This will already activate the UI commands, and actually that can be very useful in case you want to, for example, change the output file at some moment using a macro file. And also at the construction, we should also create the histograms, tuples, or whatever thing you want to have at the end. At the beginning of the run, we have to open the file, simply call the G4Analysis Manager and tell it to open the file. It's very simple, one single line. And then during the event loop, we can fill data, the histogram, the tuple, the profile, whatever you want during the event action, the step in action, whatever you need. Typically, you will accumulate some data during the event, and then in end of event action, see, in case it is a tuple, well, you will say flash the event, and with that you will close the tuple entry. But still, the run action is a good point to fill the data. If you remember the implementation that we have, the step in action updates the event action internal variable with the energy being deposited during all the possible steps during the event. And when we reach end of event action, we call the run action to tell the run action, okay, the event is done. This was the energy deposited in our target in our volume of interest during the event. And it's responsibility of, or it can be responsibility of the run action to then call the analysis manager and flash the entry, or in case it is needed, in case of an histogram, that is actually what we will do, simply fill the histogram. And then in the end of event, we have to write the data and close the file, which is literally calling the write and close functions of the G4Analysis Manager. In case you are not very familiar with the use case of the different objects that we mentioned here, so histogram, tuples, profiles, and so on, as a rule of thumb, histograms are created just for quick monitoring. We will use it now because it's rather simple and we don't need much more, while n tuples is what you will need for actual physics analysis. And of course, you are free to choose whatever format you want. If you feel more comfortable with root, you can choose root as output format. And that's all. You will see that the code that we have to implement is rather short. And with this, we will generate a histogram with the energy deposited in our target during the collection of events. Any questions? Okay, if not, we can go back to the code.
Just one more question. So using the
Yeah, so like, what is the advantage of basically using the G4Analysis Manager? Is it just like setting, let's say, a file and like reading in some, doubles or whatever, just storing it in already predefined like root or text file or CSV file? Like, is it just like memory optimized, or like, what's the advantage of using the G4Analysis Manager basically? Just like, a simpler method.
Thank you. So there are some advantages if you want to see it like that. The first one is that for this, you don't need root. You can still use G4Analysis and select root as output format, either for tuples, histograms, or whatever, but you don't need root to be installed in the computer. Neither you need to call root in the CMake list. The second thing is that G4Analysis is not just something that will simplify the way you create the output file. It is also something that will synchronize the different working threads during the simulation. You will see in a moment that we only have to change a bit the run action, including the 4 steps that we saw, and that will do the trick. Only with that, we will be able to create output files in multi-threaded. So at the end of the simulation, a single file will be created, and it will be the sum of the independent output of the different threads. And then Jam4 will take care of the synchronization. And there is a promise by Jam4, so if the multi-threading mechanism changes, Jam4 will still take care of that. If you implemented your own, there might be things that may change, or it can be more cumbersome. So as I said, I think early this week, it's better to not overcode. So if you need something simple, try to do something simple. Don't overcomplicate things. Thank you. So we go back to the virtual machine. Oh dear. Okay. So we can go to we open the virtual machine. As usual, I will increment the size. Okay, much better. So we are in the local directory. Sorry, I think I didn't mute myself. Okay. Okay, so we are in home local one. We go to the work directory. We are still in the intermediate application because we didn't move away from it. And the first thing that we will do is to start modifying the run action. So to do so, we open with gedit space dot slash source your run action.cc ampersand to keep the terminal free. This is the status of the run action as it was yesterday when we left. Please take the zip file that I uploaded to Mattermost and the Indico in case you want to continue from here. Now, the first thing that we have to do is include the G4Analysis manager.hh. And we are going simply to call the instance in the constructor. Okay. So far, not many changes. So we included the G4Analysis manager.hh, and in the constructor, we simply do like this. So now we save, we can close, or I will keep it open just in case we are still dealing with the virtual machine. So this is the lines that we modified. Okay. Now we can recompile. If I manage to minimize this. Now we can recompile, for example, using cmake space --build. And we can open our application. We have not done much actually, but you will see already a change if we open this. We can type run initialize. If you remember, we are just entering the interactive session, but the run manager has not been initialized. It means that the geometry has not been constructed. The physics list construct particle and processes have not been called, and the user actions have not been called. if we type run/initialize, so we initialize the run manager. Now we see here 3 extra directories. We see the gun directory that allows us to configure the particle gun that is encapsulated in the primary generator. And now we have here a new category that is called analysis. As you see here, we can create all these objects by ourselves. Please check the corresponding documentation in the user guide. Now we will create one histogram, but we will do it not using the UE command. We could, but we will edit the source code. Now, this was just to show you that by just calling the instance, we activate already the UE commands, the messenger of the analysis module. Very good. So we can continue editing the run action. We are going to assign a pointer, auto asterisk equal man equal G4 analysis manager instance. And we are going to create a histogram. So we will start by creating the name of the histogram name. For example, edep. We are going to assign a title. For example, jam4 energy deposited in target. Sorry. Now, the histogram will contain the number of, we will define a histogram by the number of beans and the range. I already know what we will see, so I can already tell you that we will need 100 beans, and the range of the histogram is from 0 to 10 KB. So we will define a variable G4 double a mean equal 0 dot G4 double a max equal 10 dot. And with this, we can already create a histogram. One, create H1, H name, H title, M beans, a mean, a max. If you are familiar with root, you will have recognized the syntax is exactly the same. Or the way to define a histogram is exactly the same. Very good. We can try to compile. I will keep the code open just for you to copy if you are still missing. So these are the lines. We can recompile with the same command, can recover, and we see that it compiles. Very good. So with this, we have created a histogram. We can also already ask for set.
Can we take a look at where this histogram is? How do I see that?
Very good question. So we can create an output file and we can see the output file. It will be empty histogram, but we can create it. Otherwise, it will not be seen. I think G4Analysis does not offer UE commands to see what it is being defined, but it offers a C++ interface to the map where like root, you can ask, I think it's G directory, to all the histograms that are being created in the global directory, or if it is in a file, whatever file. G4Analysis implements something similar. In our case, we will limit ourselves to simply, in addition to the histogram, put the output file name here. For example, let's start with a default name. We will be able to change it later. So we can type man pointer set file name between quotes output.root. We could omit this, and thanks to the UE command, we would have access to the same C++ function set file name, and we could put this in the macro file, or we can put it here as you wish. Very good. Now, in the begin of run action, we have simply to open the file. So we are going to copy the same line because we are going to reuse it whenever we need to access the manager. So auto space asterisk man equal G4Analysis manager dot instance. This is the way to access the instance. We will have to use it in the next function too, so you can copy it. And now we can say man open file.
So why don't we make the G4Analysis manager just a private member that we need to initialize only once? Why are we reinitializing it?
We could, but we could put it as a private member, but because the analysis manager might be a thread local, well, actually, I think it would be possible. I am not sure if it is possible. If you see the examples, you will see that in everywhere it is managed like that. It would be better practice probably to define it as a private member. Sorry, can you repeat the question? Yes, so the question is if the open file method takes an argument or not. The answer is depends. You can call it without argument, and it will open the file with whose name has to be defined before. Because if you never defined a name for the output file, it will throw an error. In our case, we are setting the output file name with this line. If we commented out this, it will throw an error. The alternative could be open file. Sorry. The alternative would be putting the file name here. However, if we do that, we are preventing ourselves from changing the output file name using a macro file. So we will have access from the UE interface to this C++ method. But if we override what we provide by the macro file before starting a simulation, and then we can provide that name, and then at the beginning of run action, we tell the run manager, forget whatever I told you using the UE command, use this other file name and open the file, it's a bit of a waste. So in general, it is better to set maybe a default file name in the constructor, and then you can use the UE command to change the output file name. For example, using a macro file. Sorry for the logging out. Thank you, John. So now we were editing just this file. So now we are in a situation in which we are creating the output file. We are giving it a name. We are creating also a histogram. G4Analysis will take care of how memory should be managed. We don't care. Now we have to change the include of the run action. So to do so, we open it with gedit./include your run action.hh, because we did something that might be good, might not be so good. We were giving an implementation of the function add event edep here in the header. We are going to delete it, so no implementation, and we are going to give the implementation in the run action. We are going also to add here as a private member a variable G4int f histogram ID. The reason is that you can create several histograms, and then it is a bit confusing how to retrieve it, how to fill them. You will see that in a moment. So we have deleted the implementation of the method add event edep, and we have added a private member called histogram ID. Very good. We are going to use it now here, because this method create h1 actually returns a number, an integer. It's just a consecutive number, it's a counter. And this will identify our histogram, so we can reuse this ID to fill the histogram later. Because we don't have access, a direct access to the histogram object itself. We have to fill the histograms by name or by this ID. And the ID is faster, of course. Good. Now we have deleted the implementation of the method add event edep. So we have to implement it again, but not this time we are going to use it. We are going to implement it in the file your run action.
Why are we using a histogram ID integer if we could just use a pointer to the histogram?
No, we cannot.
Okay.
So the question is why we are using a histogram ID instead of a pointer to the histogram itself. And it's because the interface of G4Analysis was developed to access the histograms by name or by ID. But it can be a reasonable request to get access to the pointer itself. So we are going to re-implement the method add event edep in the CC file, your run action.cc file. So we are going to type void space your run action add event edep, which is taking a G4 double edep, open close curly braces. If you remember, our current or the previous implementation was simply adding this energy deposited here. Now we are going to again call the analysis manager. So this is the function as it was before. It was simply accumulating the energy deposited over several events to calculate later the average. Now we are going to call again the G4Analysis manager, and we are going to fill the histogram. To do so, we are going to use the method fill h1. The first argument is the histogram ID. So we pass f histogram ID. And then we pass edep. So we are going to fill the histogram that we just created with this. Good. I will leave the code open. Let's see if it compiles. Yes, so the question is, the histogram should be filled event by event. Yes, that is correct. If you remember, this method add event edep was being called in the method end of event action. So sorry, in your event action, end of event. So we can check again. It is not harmful. If we open /source your event action.cc in the method end of event action. So at the end of the event, once all the primary and subsequent secondary particles are being tracked fully, we are calling run action at event edep. Before, we were simply accumulating, summing up all the energy over all the events and then dividing by the number of events to calculate the average. But now we have changed the implementation. So we will accumulate each individual energy deposited per event in a histogram. Okay, I will try to recompile just to be sure that everything is okay. Okay, does it compile for everyone? Okay. Finally, in the end of run action, we have to write the file and close it. So again, we copy this line, auto man equal G4Analysis manager instance. And we type man write, man close file. Okay. I will make the terminal, sorry, the code bigger. So in end of run action, we still have to tell the G4Analysis, please write whatever you have to and close file. Yes?
We declare the analysis manager in every method. But couldn't we have declared it in the H file, in the header file, and just call it instead of declaring it?
I will need to cross-check if that is possible. I guess it is, but I am not fully sure, so I will follow some of the examples. I will show you later. There is a dedicated directory to show you how to use G4Analysis module of Jan4, because actually offers a plethora of options, not only tuples, histograms, and so on. And I think it's very useful to take a look to it. So at the moment we can stick to that, but I think it is possible, yes, to declare a private member, and probably it's even better practice. Thank you. Good. So a final recap of how to use G4Analysis Manager. First, we need the include. Then we create the objects that we want to use. Well, first we have to call the instance, of course, because otherwise we cannot access anything. Then we create the objects that we would like to use during the simulation. In our case, we are going to limit ourselves to use a histogram, but we could also create histogram plus n tuple. We could use several files at the same time. So all of this is possible with G4Analysis, but we are not going to overcomplicate things. We are going to simply create a histogram. You can play to create a tuple. It's not very complicated. It will require only 2 or 3 lines of code extra. We provide a default file name. This file name can be overridden. You can provide a new file name using the UE command, basically /analysis/set file name, and then you provide whatever you want. This would provide some flexibility because, for example, you can change the particle GAN 2 in the macro file. So you may configure the particle gun for electrons, and you will like to have an output file that says simulation of electrons, blah, blah, blah. And if you configure the particle gun to shoot alpha particles, probably you will also like to change the output file name as simulation of alpha particles, blah, blah, blah. So otherwise, if you name all your output files as output, it will be confusing. In the beginning of run action, we open the file. During the event loop, so this method is called at the end of event, we are filling the histogram. To fill the histogram, we will use this method that takes as first argument the histogram ID. It's just a integer number to identify the histogram with the value. We could also pass a weight if we want. And finally, once the event loop is finished in end of run action, we write out the histogram or whatever objects we created, and we close the file. Very good. Do you think it will work? We can try. So we go back to the terminal. We can compile. We can try to run build or application G4run.mac. It was too good to be true. Fortunately, the error is very verbose and is telling us what we are missing. The error reads as follows: analysis W001 issued by G4 Tools Analysis Manager .merge. This is what I was telling you from the very beginning. If you put a printout, don't simply print out error without saying who is throwing the error or some information about the error. This is how a good error should be issued. The message is no master G4 Analysis Manager instance exists. Histogram profile data will not be merged. This is just a warning message, and then it crashes. Okay, as maybe I didn't put enough emphasis yesterday that each working thread now we are running in multi-thread. Each worker thread will have a copy of the run action, and the master can have a special copy of the run action too. To do so, in the user initialization, there is a dedicated method that we have not implemented yet that provides a run action. We can use the generic one to the master thread. So we have to implement this. So we have to go to your action initialization implementation. So we type gedit space source your action initialization.cc. And we have also to touch the HH. So this build method will register the user actions for the workers, but we need also to register the run action into the master. To do so, we type void your action initialization build for master, open close, const open close curly braces, and we can copy paste the line from below. So we are simply creating a run action, and then we are registering it. This build for master will create the run action for the master. This is needed because this run action will be special, will not contain any information during the simulation, and it is used just as a synchronization point when all the simulation is done. So the worker threads will be collecting information during the event loop. Once the thread finish, it will synchronize with the master thread, which has been empty, which has been doing nothing. Once the first thread finish, they merge the information into the master, and then the rest can continue when the second thread will finish, and then it will merge their content to the master, which is not longer empty, but contains the information from the first thread that merged. and so on. Okay, do you think this is enough to provide an implementation?
I think we still need to go to our application and somehow call it there.
No. So the build and build for master, so the build and build for master methods are not called by us. These are methods that are called by internal machinery of G4. We don't need to call these methods by ourselves. Do you miss something? Do you think it is correct to implement a method? Exactly. You cannot simply introduce a new method in the CC file. You need first to declare it. The declaration is done in the HH file. So you have to go back to the terminal. So we type gedit./include your user action. Your action initialization.hh. And here we had build, so we have to now declare build for master. These both methods, build and build for master, are interface methods provided by the base class G4V user action initialization. I will not tell you what are the sources of information. I think you already responded very well in the quiz, but I invite you to cross-check either the Doxygen or the source code of this class, G4V user action initialization, to read the comments that are provided there. Now we save, we close, we have to recompile still. So let's recompile, for example, with this command, cmake space ---- build space build. We recompile. Good. And now we can try to run with ./build/or application space g4run.mac. We run and it works. Now we see something slightly different with respect to yesterday. There is a third. I will try to make the terminal a bit more centered. Now, this message, if you notice, there is no prefix, as with the others. There is no prompt, and the answer is 0. This corresponds to the master thread run action, end of run action. Because we are not synchronizing by ourselves, the value is still printed, but it's not being updated. So we are not implementing our synchronization. If we use the command ls space -l, for example, or you will remember this combination of letters very often, because you will use them very often. So if you put these arguments after the ls, what you are saying is you want more details about what is going to be listed in human format, in reverse order, and temporal order. So we are going to see what is the last file to be printed will be the last file to be created. So now we see a file output.root, and this will contain, if we open it with root space output.root, and we do .ls, which is the command to open root file, to list the content of a root file, we will see this is the histogram that we created, and this is the title we assign. And we can draw it by typing dep draw. I will try to keep it open. Okay. Yes, there is.
My file was also created, but I spoke to the terminal.
Sorry, can you speak louder with the noise? I cannot.
Did you recently get any others scroll up? Oh, yeah.
Sorry, when?
So yeah, I guess this is myself. I'm getting like the default exception stuff down.
We can take a look during the break.
I'm going to draw the histogram again. You get draw.
Yes. So we are going to use root, which is another framework also co-developed here at CERN. In order to open a file, we type root space name of the output file, which is root output.root. We can list the content with .ls instead of ls, and we see that the histogram exists, and we can draw it with this line, edep draw. Very good. Yes, so the question was why the output file has a root format, and the answer is yes, because when we set the file name, we specify the extension. You can also override this option using the UE command, set output file format or set default format, sorry, and you can choose between root, CSV, HDF5, or XML. You can change it for CSV and you will see the output. Yes, the output will be in CSV. Yes, correct. Very good. So now we are going to do the final part of when developing a G4 application, which is the validation. You have to keep in mind that at the moment we have been just dreaming. We implemented a geometry, we took some reference physics, but we don't know if it is correct. Who tells us that what we implemented or the physics provided by G4 as reference physics list is correct or resembles anyhow to the reality? Nobody. And it's our responsibility to validate it. So we are going to perform the validation by comparing at least the rough validation or verification if you want. We are going to compare with some experimental data. Now we can go to the Indigo web page, and I will do it with you. And if you go to the timetable, for today, so Friday, first session, you see that there is a file with an extremely long name called x_Meroli_100 MeV _electron _5.6 micron _silicon. This contains, we can download it, we can extract it here, for example. We can take a look together. So this is the paper that explains how they measure energy deposited in silicon of different thickness. And inside you will find a root file with a histogram corresponding to the energy deposited in 5.6 microns of silicon by 100 MeV electrons, and a root script to compare the histogram that is contained in this file and the histogram that we will produce. Very good. So now we will use the terminal because I think it's good that you get accustomed to using the terminal. We are in home local work intermediate application. We are going to copy the file placed in home local downloads x_Meroli blah blah blah, and then we are going to copy these two files. We can copy them using curly braces, and we can pass a list of files. We are going to copy the compare_edep_G4 versus exp, which is the root script that will do the plot.
Where do you extract this file?
Sorry, so
You did in the.
you can, yes.
I was like, where is the zip command?
If you want to extract
No, I don't.
if you want to extract the files using the terminal, you can use the command unzip. So you have the command zip to zip a list of files, and you can use the command unzip to do the opposite. Okay. Yes. So yes, we can go to downloads. Forget about this line, okay? So in downloads, apart from the G4 trial that we were doing the first day, we have the zip file that we downloaded from the Indico. We can type unzip exp underscore and press tab to autocomplete. Now, a new directory has been created. Sorry, not directory. The files are already unzipped in this directory, and we can copy them using the command cp. Or if you feel more comfortable using the mouse, please use the mouse. There is no reason to suffer. not too much, particularly on a Friday afternoon. I will use the terminal. I will go back to the work intermediate application, and I will copy the files by typing cp home local one downloads, and we can use curly braces to copy several files in one shot. So we can copy. We can copy these files, the .cxx, which is a root macro to do the drawing, and the file exp meroli 100 mb blah 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 .root, and we are going to copy it here. Very good. As a final step before running the validation, we are going, or verification, be more correct probably. We are going to edit the file G4run. Instead of 10 events, we are going to run 10,000 events. Okay. I will leave it open. So I will also add a comment here just for people that might join later. This is the file G4run. Okay. Okay, and now we can run it with ./build/our application g4run.mac. Did you produce an output file?
How was it so fast?
Don't worry, there are ways to make it much slower. The question was why it is so fast. We are using the default physics list, which is default because the less accurate electromagnetic physics list, but it's also the fastest. We will see the comparison. So now, yes.
In the output, there are two average number.
Yes.
Two average energies.
Yes.
One from one thread and the other one for another thread.
Yes.
In the histogram, you only have one histogram. I guess the merge command work there automatically.
So, yes, thank you for your question. So let's say we left the implementation of calculating the average energy in a half-finished state. It works in sequential, but if you want to make it work in multi-threading, you still need to implement some few other steps. We will need to implement our own class derived from G4run, for example, called your run, and then we have to accumulate the energy and whatever other property we want into this object. Then we have also to implement a method of this class, which will be merge, and this merge is automatically called by Jam4 whenever the thread finish. Because this requires a lot of much more code than this, I decided to use G4Analysis. So we left the implementation using custom G4Run object aside. You can see the code from previous years because it's available in the GitHub. You can, it's full of comments, and I believe it's very easy to follow. But G4Analysis for this case is more than enough and requires much less code and understanding of how actually Jam4 works inside. In the advanced course, you will have much more details about the multi-threading schemas because Jam4 offers several. And the reason, by understanding how Jam4 works internally, you will understand better why you need to implement your own G4Run object. But I prefer to code less and still do the validation. Thank you. Okay. Thank you for the question. We are going just to open the script. I will do it for you. You don't need to do this. So we are going to open, I am going to open the root script that we are going to use to compare EDEP G4 versus experiment, just to see what it is inside. It's rather simple, like 20 lines of code. This is just declaring a function that is taking as argument the file that contains the output histogram that we just created with Jam4 and the name of the file with experimental data. Then we open the Jam4 file, we retrieve the histogram, we scale it because the one provided by experimental data is already normalized in this case. We open also the file in case of the file with experimental data, we retrieve the histogram. Actually, this line is not needed, but okay. And then we draw it very well. Now, if you all created the output file with the 10,000 events, very good. So now we can type root compare EDEP G4 versus x.cxx. You can use the tab and hopefully it will work. Okay. Do you see any problem here? And can you think why? The geometry is different because we are not touching the geometry. So the default is still, the material is silicon, but the thickness is 1 centimeter. And also the particle gun was configured to be electrons at 100 MeV, or it was something else? So we have to change this. We are still in a moment when we cannot change all of that using the UE commands. So we still have to change something in our application.cc. We open the cc file. And here after detector, if you remember, we implemented a method that was, so this is the file or application.cc. We have a method that is set target thickness. So we are going to hard code. This is not the best practice. This is just for the moment to do the validation before the break. And we are going to put, so detector point set target thickness, and as argument, we have to provide the same thickness as in experiment. That was 5.6 micron. So we type like this. I am going, okay, I will leave it open. So this is the line that we just added. I am going to recompile. We are going to run again. And we can plot again. Okay. Did everybody understood what we did? Sorry, and I forgot something. We changed the geometry, but still the particle gun is not configured as in the experiment. So we have to change the file G4Run to configure the particle gun. To do so, we use, gun particle E minus, that is okay. Gun energy, because this didn't change. look at. So we have to change the energy. In this case, we are going to use the UE command that the G4 particle gun messenger offers us. So we add this command. So the two changes to make the comparison with the experiment were, in our application, we have to change the thickness because we still do not have a UE command. And in the G4 run, we have to change the energy. Good. We can run again. Now a new file will be produced. And if we run the comparison, it goes to nowhere. Where is the experimental data? Hidden. Where is it? We didn't follow all the good practices that we were reviewing all these days, and this was not a quiz question. What are we missing? The units. The default units of Jan4 are MeV, but here we should be plotting kV. If you remember, when we defined the histogram, we said that the energy should be kV, but we were not dividing by kV. Very good observation. So we have to go back to the implementation of the run action. So gedit source your run action, and we can cross check. So we said explicitly range of the histogram between 0 and 10 kV, but then here we were simply filling the histogram without saying the units. You will see this mistake all over every framework that you use every time you have a program. The units are very simple, but they can create authentic messes.
Where did we say that it's going to be in kV? No, where that it should be in kV?
We say that here.
Okay.
Because the axis is already in a fixed unit. For example, if you say that the range of the histogram is between 0 and 10 natural units of energy of Jan4, very well. But it is not. We specified kV. So we have, if we want to score kV, we have to divide here by CLHEP kV. You have, every time you interact with Jan4 and you want a magnitude in certain units, you have to divide by the units. If you are providing Jan4 with a magnitude in certain units, you have to multiply by the corresponding unit. And also, just to mess more, I remind you that the system of units of root, Jan4 and others do not match. So you have to be extremely careful if you are working with both at the same time. Very good. So now we save. And again, we recompile. We are missing the include. So we have to go here and include G4 system of units.hh. Okay, it compiles. We run. And now we can run root, compare script again. And now it looks better now. Eh? But still we could make it look even better. Just before the break, we will do just a quick change. In order to make it look better and just 2 changes for you to know, we are going to edit once more the OR application when we were saying the physics. And now we are going to change slightly the physics. So we are going to add a suffix that is underscore EMZ. As I told you, Jan4 provides a set of physics lists. In particular, there are many physics lists regarding the electromagnetic physics. So far, we have been using EM0, the so-called standard electromagnetic physics level 0, which is, I think, the fastest, but also the least accurate. So if we want to use the most accurate electromagnetic physics list in Jan4, we should change it to this when we are retrieving the physics list from the factory. Now we have still to add something else. In the file G4 run, we are going to type run set cat 1 um. This is a property that will be mostly honored by electromagnetic processes. And if you want to know more about this, which is super important, please take the advanced course. At the moment, we will just use it blindly. Okay, so now we have to still recompile again once more because we changed the physics list, which is hard-coded. We have to run again once more, blah, 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 blah. And we are going to open it again. And now the agreement is much more decent, I would say, right? Very good. Very good. And just before the break, so you will have something to think about. There was a bug in the application and nobody noticed so far because it's not a bug that will be obvious during the compilation or during the run. These are the worst kind of bugs that you will see ever. It will give you an output, but the output will be wrong. You don't have to do this. I will do it for you. So I will change the material. Set target material. G4 uranium, for example. You saw that I did actually two things here. Anyhow, let's see what happens. We are going to run. Do you think the result will be the same or it will be different? Should be different. Bloody hell. Okay, and now we can take a break. You can think during the break why the method set target material didn't work. After the break, we will implement custom UE commands and we will fix the bug, by the way. If there are no questions, of course. There are questions? Okay, let's go for the break. Thank you.
Yeah, let's reconvene in 5 to 4.
5 to 4. Okay, thank you.